Welcome back, MAT152 students. In this lecture, I would like to take a look at how do we go about determining parameters from sample statistics. And in this lecture, we're going to talk about confidence intervals and how do we develop confidence intervals, what are they, and so let's get started. So here's the idea that we need to develop. A simple random sample of 100 fourth graders is selected to take part in a new experimental approach to teach reading. At the end of the program, the students are given a standardized reading test, and on the basis of past result, it is known that scores on this test have a population standard deviation of sigma is equal to 15. What we'd like to do now is to develop some idea of what the population mean is. In this case, I've got the population standard deviation from past studies, but where do I get started on developing what the population mean is? Well, we're going to need something to get started with, and that's called the point estimate. And we're going to see this over and over as we go through chapter 7. So the point estimate that we're going to use is we've got this sample of students that we've worked with, so we're going to start with them. The sample mean score for the 100 student was X bar, that's the sample mean, is equal to 67.30. So the administrators want to estimate what the mean score would be if the entire population of fourth graders in the district had enrolled in the program. The best estimate for the population mean is the sample mean. That X bar is equal to 67.30. That sample mean we're going to call the point estimate because it is a single number. Naturally, if we had other samples, that sample mean would be different values. So when we develop this interval, if you will, then it's going to be based on a center and then some skewness away from there. So it is very unlikely that X bar is equal to 67.30 is exactly equal to the population mean mu of all the fourth graders. Therefore, in order for the estimate to be useful, we must describe how close it is likely to be. We could possibly think that it's just off 10 points. Well, we would estimate mu then with the interval 57.30 less than mu, less than 77.30, which could be written the very same way as here's my 67.30, that's the sample mean, plus or minus what we think it would be off by. That plus or minus number is frequently referred to as the margin of error. So, but suppose that we want a better idea than just something that we've come off with off the top of our head. Anybody could come up with one, and it would be all over the place for everybody. What we would like to do is develop some repeatable method that we can come up with an interval where the true mean would be somewhere in there, and we could say it with some confidence. So let's say, and our confidence is going to be naturally from 0 to 100%. Okay. Suppose we want to be 95% confidence in our interval. That 95% is the most frequently used as a starting point. So if you hear of some survey of here's some proportion of people with a margin of error, they're usually talking about a 95% confidence. So I'm going to start off with, I'm going to use that sampling distribution of X bar. So remember, this is where last week, or the last chapter, we talked about sampling theory. So so if we take sample sizes that are large or normally distributed, that if we keep taking samples and samples and building a distribution based on the sampling, this is what this looks like. The mean of the means is the mu, and the standard deviation of the means is the sigma over the square root of n, and now we're going to start calling this thing as the standard error. So here is what it was for our reading example. The standard error is, here's our standard deviation, the 15, divided by the square root of n, which is 100, that's going to be 10. 15 divided by 10 is the 1.5. So this is the standard error. We now construct a 95% confidence interval for mu. So we're going to start with a normal curve, and we're going to develop z-scores that bound the middle 95%. So all we're going to do is look, whatever that confidence interval we want, at that confidence, we're going to say, okay, here's the inside area, and then we're going to find these values here that limit those areas from the inside 0.95, 95% to the stuff outside. So if we were inside 0.95, the stuff on the outside, everything is 1, so that must be 1 minus 0.95, or 0.05. It's symmetric in these tails, so we divide that by 2. Half of it over here, half of it over there. 0.05 divided by 2 is the 0.025. So now if we do the inverse, we go into our tables, standard normal, we go look for area 0.025, and the standard normal is going to have area to the left. So if we go here and look for this 0.025, we come out with negative 1.96 as a critical value. These things are called the critical value. And all I want is really that positive version. So I just drop the negative, and my critical value is going to be the 1.96. Now I can calculate the margin of error. That's just the critical value times the standard error. Remember, the standard error was this up here, the sigma of the square root of n. Multiply these together, and that gives us the 2.94. So a 95% confidence interval for mu is therefore x bar plus or minus the 2.94, the margin of error. Our mean from the sample was 67.30 plus or minus 2.94, and that gives us the 64.36, 67.30 minus the 2.94, and then 67.30 plus 2.94 gives us the 70.24. And the way we communicate this result is saying like the following. We are 95% confident that the population mean, that's what we are estimating, is between 64.36 and 70.24 between the two. And that gives us an idea of everything. We're talking about the population mean. We developed it based on 95% confidence in our picture. And here is the values that we've come up with. So basically, this is kind of a picture of what we're doing, this confidence level. If we build it, it's made up based on different samples. Notice if we'd have done a different sample, our X bar is going to be different values. But this is going to give us a coverage if we did mu plus or minus. So if we did here, if we did this X bar, we're still going to get coverage over here, over there, but this may be all the way at this end. It may be all the way at this end, but that kind of gives us a place to start with. So if we were to draw many samples and use each one to construct a confidence interval, then in the long run, the percentage of confidence intervals that cover the true value of mu would be equal to that confidence level. So here's our terminology that we've kind of developed, and let's go back over this thing. The point estimate, we're going to use, this could be anything. This could be the sample based on the sample mean, the sample proportion is the ones that we're going to work with here. A confidence interval is an interval that is used to estimate the value of a parameter. So that confidence interval is going to be based on some confidence level. We've got to get critical values based on that confidence level, and then we find the margin of error is computed by multiplying the critical value by the standard error. So for the one that we are developing now, when we know the population standard deviation, we're always going to use the standard normal table to get our z-scores. Here is some very popular ones for the confidence level, and we can kind of go ahead and write these things down all the way up. 95% is 1.96, 98, 2.326, 90 is 1.645. So these will be fixed. Now, if we wanted to go and do a 92%, then we got to go back through that procedure. But for here, all of these are going to be fixed, and we can kind of continue to use them as long as we use the standard normal. So let's work an example. A large sample has mean x bar is equal to 7.1. A standard error of sigma over the square root of n is equal to 2.3. So they've done this calculation for us, and they built the standard error. Construct a 90% confidence interval for the population mean mu. So we go to that table, look for 90%. Our critical value is going to be the 1.645. I multiply the critical value times the standard error to give me the margin of error. That'll give me 3.8. And then I use my sample mean plus or minus that margin of error to give us a 90% confidence interval of 3.3 less than the population mean 10.9. So the population mean is squeezed between 3.3 and 10.9. And we would communicate it by saying with 90% confidence, we can say that the true mean mu lies between 3.3 and 10.9. So this notation is usually what is given in the formulas. So we will need to find these critical values, and they use this Z alpha notation. So sometimes we may need to find the critical value for a confidence level not given table A3. To do this, it is useful to learn a notation for the Z-score with the given area to its right. Okay. The notation Z alpha refers to the Z-score with an area of alpha to its right. The notation Z alpha over 2 refers to the Z-score with an area of alpha over 2 to its right. So these are the positive versions, is what they're talking about, the area to the right. This is very symmetric. If you had the very same area to the left, it would be a negative value here. So if I start out with a confidence level of C, 1 minus C is the alpha, and they're just saying that here 1 minus alpha is the confidence level. They're both the same. 1 minus C is alpha, 1 minus alpha is the confidence. So here's the Z alpha over 2 because I've kind of split this up into both sides over here. Okay. The area between the negative Z alpha over 2, Z alpha over 2 is 1 minus alpha, or that's just the confidence that we're started with. So here's an example of finding that one of the critical values that's not in that table. And we'll use this frequently, and in the next section, we've got to do this each and every time. Okay, I want to find a Z alpha over 2 for a 92% confidence interval. So here is the 0.92. This is where I start with. This is where we always hear. And then I say the area to the outside is 1 minus the 0.92. So this is why they kind of start with this formula, but you can start with the 1 minus C as well. 1 minus C is the 0.08, that stuff outside of that middle, and then we take half of the 0.08, that gives us 0.04 to the left, 0.04 to the right, and then I go inside to find that area to the left. So here they wanted to work with the right, which is fine, and they're just saying if everything is 1 minus 0.04 gives me 0.96. So if I go into the table and find the area to the right, or to the left be not 0.96, this is the closest. My Z-score is 1.75. I can also use the TI to do the inverse normal and say I've got 0.96 area to the left. The mean is 0, standard deviation is 1, gives me the 1.75 as the critical value that way. Okay. So some assumptions to go along with that. We need to have a simple random sample. The sample size is either large, n greater than 30, or the population is approximately normal. Remember, this is the criteria to get the sampling distribution to be normal. And let's go through one of these things and build it all the way. So a machine that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25. It is known from past experience that the fill weights are normally distributed with a standard deviation of 0.2 ounces. So we're going to construct a 90% confidence interval that for the true mean. Known from past experience that the fill weights are normally distributed. Okay, so we've got those. We meet the assumptions. And we're going to find the critical value for the or 90%. So I go into my table that we worked with earlier. Here's 90%, 1.645. That's our critical value, and here's all the other stuff. So we're going to have to find the standard error, sigma over the square root of n. That's the 0.2 divided by the square root of 6. That gives us 0.08165. The margin of error is that standard error times that critical value, and that gives us 0.1343. Notice if we look up here, the more confidence I am, the bigger the critical value is. So if I was only 80%, this would only be 1.282. At 98%, this is 2.326. So this is the number that's changing. This is going to be bigger, so this margin of error is going to be bigger for a greater confidence level. That's opening up our interval, but we're more confident that it's in there. So now we build out our interval. Our x bar plus the 0.1343, that's that margin of error from here, or 20.25, that was our sample mean, plus or minus this 0.1343, that's 20.12, less than mu, less than 20.38. So we are confident, 90% confident, that the mean weight mu is between 20.12 and 20.38. Now notice, I'm going to go back. Let's see if I go here. It's supposed to put 20 ounces of cereal in each box. So we've got here between 20.12 and 20.38. So it looks to be a little over. At that confidence level, it looks to be a little over than 20 ounces. Okay. So here is, we can also do this with the TI-84 Plus. We can go into our stat, pressing stat, highlighting the test, going to for the Z interval. That's because we're developing an interval, and based upon the normal distribution z-scores. Okay. We'll just go in here, select this, and then go through and basically say, here is the sigma, our sample mean, the n, the sample size, and then the confidence level, the 0.9 was the 90%, and then just do the calculate. So if we did that, we get our value, and then this will give us directly, this gives us the Z interval directly of the 20.116 to 20.384. So this is an open interval. It almost looks like a coordinate if you're used to graphing coordinates, but it's not. It's saying here's the interval between 20.116 and 20.384. That's the confidence interval. So again, here is the confidence versus margin of error. If we want to be more confident that our interval contains the true value, we must actually increase the critical value, which increases the margin of error, and there's a trade-off. We would rather have a higher level of confidence than a lower level, but we also would rather have a small margin of error. You would like to have a very small margin of error. There's some mean plus or minus a small value. I can only do this by reducing the confidence level. The more confidence I am, I actually open this thing up to make sure that within this, that 99% of the time, we're going to get that true mean. So the diagram presents 100 different 95% confidence intervals. When we construct a confidence interval with level 95%, we're getting a look at one of these confidence intervals. So here's the confidence intervals, all based on different ones. And most of the times that we're going to get that true mean. So this would have been the true mean. Here would have been a confidence intervals that we developing. Some of these may not capture, but we should be able to. So we don't get to see any of the other confidence intervals, nor do we get to see the vertical line that indicates where the true value mu is. We don't know what this is. We just know that if we did 100 samples, this is what the confidence intervals that we calculated. What we do know, though, is that our confidence intervals was constructed by a method that succeeds 95% of the time. The confidence level describes the success rate of the method used to construct a confidence interval, not the success of any particular interval. So our next step in this process is what about if we wanted a particular margin of error at a particular confidence level? What sample size would I need to do to get that? Okay, because I'm dividing to get the standard error, the sigma divided by the square root of n. So I've got some play with the standard error. The bigger the sample size, actually the smaller the margin of error. Okay? The standard error is going to decrease, the margin of error decreases. Okay? So here was our margin of error, and we're just going to do a little m. Sometimes I use ME for this, the margin of error. But the m is, there's the critical value, there's the standard error, and I'm actually going to solve for n here. Put the m down here, this is over here, and then square both sides. That's my formula for the sample size needed to achieve a particular confidence level with margin of error. So if the value being given in the formula is not a whole number, round it up to the nearest whole number always. That way, by rounding up, we can be sure that the margin of error is no greater than the desired value of m. Okay. So what would we need? So we want to estimate a mean weight of mice after they have been fed a special diet. A previous study has known that the weight is normally distributed with standard deviation 3 grams. How many mice must be weighed so that a 95% confidence interval will have a margin error of 0.5 grams? Okay. So here's our formula. We need a 95% confidence, so we go and look at our table or do inverse to get our critical value. That's the 1.96 for 95% confidence. A margin of error I want to be with a 0.5. The sigma was 3. That's known from previous studies. So the number we would need was 138.30. So I need to round up to get 139. That's our sample size. Okay. So we must weigh 139 mice in order to obtain a 95% confidence interval with a margin of error of 0.5 grams. Okay. So I'm going to wrap that up here. We're going to continue with this concept, but we're going to do it in 7.2, where we're going to look at what if we don't know what the population standard deviation is. That's going to be a more realistic version of what we've got. We start with we want to know something about a population. We have no idea what it is when we're starting, so we're going to go grab a sample and use that to develop a confidence interval, and then we have to use the S, the sample standard deviation. So we'll see you next time. Have a good day.